Hi, welcome back to a new lecture from Transformers for Vision series. In today's lecture, we'll be discussing about contrastive learning. The main reason why I wanted to introduce this topic in a separate lecture is because of its importance in models like CLIP. So CLIP was probably the most famous vision language model that utilized the idea of contrastive learning. This paper is cited highly. In the last lecture, we briefly discussed not about the paper, about the existence of the paper. And one of the co-authors you might recognize by name Ilya Sutskever. So this paper came out from OpenAI, and at the moment it has 46,000 citations. But the idea of contrastive learning itself for images, it was popularized by this paper, which came out slightly before this. So the contrastive CLIP paper, which was contrastive learning for vision language models, was introduced in 2021. But 1 year before that, there was another paper which introduced a simple contrastive learning framework. And this paper has almost 28,000 citations now. And this paper really revolutionized the way the idea of contrastive learning was implemented for image text dataset or just image dataset. So let's see what does contrastive learning simply means. And the idea is simple. The mathematics is also simple, but its implications is very huge. And that is one of the reasons why the CLIP model became so popular. So we'll be briefly discussing about CLIP paper also today, although entire paper review we'll have to put it for some other lecture because the paper is very long. But we'll see what does contrastive learning mean and why is it so important for vision language models. So with that, let's get into the lecture. Before I move forward, let me briefly discuss what we saw in the last lecture. In the last lecture, we discussed about basics of vision language model. A basic vision language model will have an input embedding for text. So this diagram is what we essentially had a look at last lecture. We will have an image encoder for image inputs. We'll have a text encoder for text inputs. And optionally, there will be a fusion block. Now, this fusion block can be a transformer architecture itself. So it can be a combined attention between concatenated image and text embeddings, or you can have cross attention where queries in the text attend to key and value in image, or rather query attends to key from image, and then that is taken as a dot product after taking Softmax with the values from image, or vice versa. Query will be there in the image, keys and values you consider from the text. So this is what we essentially discussed in the last lecture. If you want to go through the basics of vision language model in detail, I highly recommend you to watch the previous lecture. And here is an example of how VLM workflow looks like. So first, your input image will be converted using the image encoder into visual embeddings. Each embedding is a vector. And then the text encoder will convert your text input into a vector. And ideally, these two vectors should have, if they are in the common representational space, they should have vectors that look similar. So this image that we looked at in the beginning, this was called joint embedding space or joint representation, where this image that looks like a dog running towards the camera and the text that says happy dog running towards the camera, if you convert those into vectors and if you are just drawing the tip of those vectors by these dots, these two dots, one is the green one is the image representation in vector format, red one is the text representation. They are both very similar. The cosine similarity between those two vectors will be very, very high. There was one more diagram which we discussed in the last lecture, and here you can see that it's an n-dimensional space where we're just showing 2 dimensions. And in general, vectors have semantic meaning. So vectors for animals, let's say dog and cat, they will point towards the similar or common semantic space for animals. Vectors for apple, orange, etc., they will point towards the semantic space meant for fruits. And the cosine similarity between vector embedding of dog text and vector embedding of dog image will be very high. They'll be very similar, those two vectors. So this is essentially what we discussed in the last lecture. But we did not discuss too much about what kind of losses can we construct based on this vector embeddings. Are we going to compare the embeddings directly? And that is one way in which you can do, as you can see in this image. So this image shows probably the simplest version of vision language model, also known as dual encoder. So you will have an image converted to image embedding using image encoder. Text will be converted to text embeddings, and then you compare those two embeddings to construct a loss. And this loss function, this can be like a clip style loss or contrastive loss, which we are going to discuss in today's lecture. And another example that we discussed was called as early fusion, where before you have an attention block, your both embeddings will be combined. It will be fused into one single representation. In that one single representation, you will have image as well as text data. So whatever comes out of the fusion block will be a joint representation. Following this joint representation, you may have just a multi-layer perceptron, which is a feed-forward neural network, or you have a transformer block that learns attention weights based on the joint representation. And then finally, if we are trying to do, let's say, image retrieval, you will do a softmax classification where the output is for corresponding to this image, this is the best caption from your data set. Or you can have visual question answering, or you can have image captioning. So all sorts of language plus vision tasks are possible. So this is in a nutshell what we discussed in the last lecture about vision language models. And in today's lecture, now let's see what exactly is contrastive learning. The main idea behind contrastive learning is to maximize the similarity between what we call as positive pairs and minimize the similarity between negative pairs, or basically it should be as dissimilar as possible. So let's see what this means from the contrastive learning paper itself. So if we just Google contrastive learning and just look for images, there is one nice image which shows this idea perfectly. So have a look at this. Let me copy paste this image. So just have a look at this, okay? So this is my anchor, meaning the image that I'm considering right now, the middle image of this dog. This top image is just an augmentation of this image. So this is also, you can, as a human, you can see that it's exactly same image, except it's black and white. And this is called as a positive pair. So these two images are now positive pairs because you are performing some sort of transformation to construct this positive image. On the other hand, if you consider these two images, these are negative pairs because this is a completely different image. It's not the same animal. Now what you want to do is you want to construct a distance function between these positive pairs and negative pairs, and your end goal is to minimize the distance between positive pairs and maximize the distance between negative pairs. So then the anchor image will be fixed, and then anchor image will be compared to bunch of negative images. Anchor image will be compared to positive image, and you want to maximize the distance with positive pairs and minimize the distance between, or vice versa. You want to minimize the distance between positive pairs, maximize the distance between negative pairs. This is in very simple terms what we are trying to accomplish. Now, if you look at the contrastive learning paper, I'm not talking about the clip paper, I'm talking about this paper for contrastive learning. They have a little bit intimidating kind of diagram here in figure 2, which I have pasted here. What this is showing is very simple. You start with your anchor image, and from your anchor image, you construct positive pairs by performing transformation. So transformations, they are representing as T prime or T. So these are two different transformations to produce two transformed versions of the same image. Now, what are some examples of transformations? One could be converting the color scale from RGB to black and white or grayscale. One could be random rotation. One could be random flipping. You could be imagining random cropping. So I'll come back to this figure 2, but let me show you some examples of transformations that are discussed in the paper. So this is the original anchor image, cropping and resizing. So here you crop out one portion and then zoom in to resize it back to, let's say, 224 by 224 or whatever. Here you are cropping and flipping horizontally. Here you are converting to black and white. Here you are changing the color, the whole color itself. This is a rotation, or you are eliminating some portions by adding a overlay rectangle with a certain color. adding Gaussian noise, adding Gaussian blur, or Sobel filter for detecting edges. So these are all different transformations that you can apply to your original image, and all these are positive pairs. This and this is a positive pair, this and this is a positive pair, because essentially they are all the same images. So now a model should be able to tell that even if you input these two images, a model should be able to say that these two are essentially positive pairs, or they are very, very similar. And this is, if I remember correctly, it's figure 3 of the paper. Yeah, so, or rather figure 4 of the paper. So this is what is showing the data augmentation operators that this paper was studying. Now let's come back to figure 2, what the figure 2 was trying to say. Figure 2, a simple framework for contrastive learning of visual representations. Two separate data augmentation operators are sampled from the same family of augmentations. Now, what are same family of augmentations? If we are doing something to the image in terms of appearance, in terms of the whole image, so we could just crop the image, right? So the content inside the image remains the same. You could just flip the image, rotate the image, or you could add jitteriness to the color. You could add blur. These are all transformations belonging to the same family. Another set of transformations that can belong to the same family is rotation with different degrees of rotation. So 10-degree rotation clockwise, it's one type of transformation. 30-degree rotation anti-clockwise, it's another transformation. They are all belonging to same family. So it doesn't matter as long as you are applying transformations belonging to the same family. They are all positive pairs. So what this image is showing is you construct two augmentations of your anchor image by performing transformations from the same family or augmentations from the same family, and it is applied to each data example to obtain two correlated views. What do we mean by correlated views? Because ultimately we are seeing the same image of the dog, but it might be two different views. This is like a zoomed in view. This is a zoomed in and a little bit to the side, that kind of a view. This is a flipped view here, and this is also a rotated view, right? And they are discussing about two types of views, global and local views, global and local, and adjacent views, where essentially you are looking at two different parts of the same image that are adjacent. A base encoder network F and a projection head G are trained to maximize the agreement using contrastive loss. We are yet to discuss what is contrastive loss, but let's come to that by first discussing what is positive pair and what is negative pair, because in the contrastive loss formulation, the idea of positive and negative pair is anyway going to come. So this Xi is transformed into Zi. So now this you can think of as an embedding in simple terms. So this is embedding of Xi, and this is embedding of Xj. And how do you get this embedding? You first go through a base encoder network, so that is F, and then you go through a projection head G. So projection head projects this encoded Hi and Hj into some space. So essentially you can think of these two as vectors. So vector corresponding to I, vector corresponding to j. What are I and j? I and j are two different transformed or augmented images which resulted from the original anchor image. And now the goal is, since these two were produced as a result of augmentations belonging to same family, you want to maximize the agreement between these two, or if you construct a distance function, you want to minimize the distance between those two, right? This is what you want to do to kind of bring positive pairs closer to each other and negative pairs farther from each other. And to maximize this agreement, you can use something called as contrastive loss. One more detail here to mention for this specific figure is that when we are doing downstream tasks after training this model, we don't use the embedding Z, we rather use the embedding H, meaning whatever embedding is constructed just by using the encoder network. So this projection head is removed during the further downstream tasks. This is just one additional detail that is mentioned, so I just wanted to just say it out. Now let's see how the contrastive loss look like mathematically. So we have three items to consider. We have positive pairs with respect to anchor. Anchor is your original image. From anchor, you perform augmentation to create positive pairs. That is one way to create positive pairs, but you can have positive pairs just because of the existence of images that are very similar in a data set. And you have negative pairs also in the image data set, which are completely different images. Now, what you want to do is you want to construct a loss function where if this distance, let's say if this cosine similarity is not so good, then you should penalize the loss function. Basically, the loss should be high, right? Because ideally, positive pair with respect to the anchor should have very high cosine similarity. So if the cosine similarity is low between positive pairs, then it should result in high loss. Similarly, if there is a negative pair with respect to anchor, and if their cosine similarity is high, that is also a bad thing. They should have low cosine similarity, which means if their cosine similarity is high, that also should result in a very high loss. So let's see from the perspective of a positive pair, how can we construct this mathematically? Now look at three vectors here. So this vector we can call as Zj. Zj is any other vector in your data, and Zi, let's call it as the anchor. Now, here what is mentioned in this, what we see is we are using Zi as the symbol for embedding. So we trained a network to produce the embedding, and this embedding has you can compare the embedding for one transformation against another, or you can compare that embedding for two positive pairs, or you can compare the embedding between two negative pairs. For positive pairs, embedding should result in high cosine similarity. For negative pairs, low cosine similarity. Now, how does this mathematically look like? Firstly, what is cosine similarity? It is dot product between normalized vectors. So if Zi and Zj are the vectors, we can normalize Zi by dividing by modulus of Zi. So this will become a unit vector. You can normalize Zj by dividing by modulus of Zj. So this is now another unit vector. And when you take the dot product between two vectors, it is AB cos theta. So now if theta, so let's say A dot B, where A and B are unit vectors, will be AB cos theta. And since magnitude of A and B are both 1, this is basically cos theta. So this is cosine similarity if these are unit vectors. Otherwise, you can normalize them. Divide this by modulus of A, divide this by modulus of B. Now, what is this cosine similarity? It means if theta is 0, cos of 0 will be 1. If theta is 90, it will be 0. So if the angle is very close to each other, if those two vectors are pointing very in similar directions, they will have very high cosine similarity. Now here I is the anchor and j is the remaining vectors in your data set, correct? So let's consider how the similarity will look like. So I is the anchor. So I is the anchor, and then you have bunch of j values. So let's say it goes from 1, j can run from, let's say, 1 to n, because there are n number of images. Now the similarity between ith image and image number 1 will be something, ith image and image number 2 will be something else. You don't compare I with I itself, obviously that will be trivial. So here you consider all the images except I itself, and you construct similarity scores by taking dot product between I and 1, I and 2, I and 3, etc. up to I and n. So you can call this dot product as a similarity function, because either you can take a simple dot product without normalizing, or you can convert it into cosine similarity scores by normalizing. And let's call it as a similarity function sim. Sim of zi comma zj is simply cosine similarity between zi and zj. Now we will have how many pairs here? We will have n minus 1 pairs, because I and 1 is a pair, I and 2 is a pair, I and 3 is a pair. I and I is not a pair, because obviously between image I and image I itself, similarity, cosine similarity will be high. So we don't care about that. So we'll have n minus 1 pairs, right? So if we plot the cosine similarity values between these vectors, how would that look like? It will look something like this. The cosine similarity between I and j will be the highest So let's say this is I, this is J. Let me reduce the pen thickness. This is J. And let's say I and J are positive pairs. This value will be the highest cosine similarity score. The cosine similarity between rest of the items, which are usually negative pairs in these kinds of data sets, should be very low. So this is what we want. So y-axis is cosine similarity and x-axis is which pairs we are considering. Is it I and 1? Is it I and 2? Is it I and j? Now this is just the vanilla cosine similarity. The better way to convert this into sort of like a probability distribution is to take softmax. So what if we took softmax of this similarity score? What is the softmax formula? Softmax formula is e raised to zi divided by sigma e raised to zi. And how would this look like if zi were the cosine similarity scores? It will look like e raised to similarity score between zi comma zj, which is the cosine similarity or dot product similarity, divided by sigma e raised to similarity between zi and let's call it as zk, where k runs from 1 to n, but k should not be equal to I, because then this will be zi and zi. So k is not equal to I. Now here, if I and j is a positive pair, this we can call as sort of like probability score for positive pair or correct pair. Because pairs that are very similar to each other, they should have a high softmax probability score. So what will happen if I take softmax of a graph that look like this? Then what will happen is all these smaller numbers will get suppressed. All the bigger numbers will increase in magnitude. This we can easily see by plotting it on a Google sheet. So let's try that. So in this Excel sheet, I have constructed 3 numbers. So let's say these are the 3 similarity scores that we are currently considering, 0.1, 0.2 and 0.8. We can say it's the similarity score between Z1 and Z2, Z1 and Z3, Z1 and Z4. If we plot the similarity score just like that, this is the resulting plot, this red color plot, 0.1, 0.2, 0.8. Now, once we convert this into softmax, we get a plot like this, and this will add up very nicely to 1. So 0.24 plus 0.26, it's roughly 0.5, and this is 0.49. So sum up to 1. So this probability distribution will be such that all the numbers will be between 0 and 1, and they will nicely add up to 1. On the other hand, these similarity scores, cosine similarity, need not add up to 1, because it can be different depending on the cosine similarity between individual vectors. So that is one reason why we are using softmax, but there is actually one more reason which I will show you in one moment. So now let's get back to the formula. So if we are taking softmax of all these similarity scores, we can say that the softmax probability corresponding to the correct pair. So let's say the correct pair is zi and zj. So correct pair means the pair with the highest similarity. The probability score, softmax probability score corresponding to that will be exponent of cosine similarity between those pairs divided by exponent of cosine similarity between the anchor and all the images or all the data points in your data. Here the only thing is k should not be equal to I, because you are not considering the dot product similarity between I and I. So this zi and zi should not come. So everything except I. So in the denominator, now you are considering exponent of similarity scores between not just the correct pairs, all the pairs. Now, how do you convert this probability into a loss function? Because just imagine, what is that we want? What we want is for correct pairs, if this is the probability score, we want the loss to be highest if the probability score is lowest. So if the correct pair score was low, so let's say this softmax probability was, let's say, close to 0, let's say 0.1 rather than 0.9. So 0.9 is closer to 1, 0.1 is closer to 0. So if it is closer to 0, I want my loss to be high. If it is closer to 0.9, I want my loss to be low. And what is the function that can allow us to do this? You simply take a negative logarithm of p. What is negative log of 0.1? So logarithm of 0 is negative infinity. So logarithm of 0.1 will be a big negative number. So negative of negative will be, this will be like a big positive number. Big positive number. And what is negative log of 0.9? Negative log of 1 is 0. Logarithm of 1 is 0. So negative log of 0.9 will be a small positive number. Small positive number. So then what is our loss? Our loss is negative log of p, which is equal to negative log of exponent of similarity score between zi and zj. And then the denominator is sum over all pairs of I and k, where k is not equal to I. So this will be exponent of cosine similarity between zi and zk. This will be the loss function. And this is exactly like clip loss or contrastive loss. There is one more term which I want to introduce, is an extra term for sensitivity. This term is called temperature or tau. And this tau term is used to scale the similarity score. Let's see why this tau term is useful. So first of all, let's go back to our plot and let me change this value to something like 0.2. Now my graph is like this. See, the highest number, which was 0.8, is staying highest. But here, because these numbers were distributed in 0.1, 0.2, 0.8, etc., my softmax score distribution is not very sharp. In fact, the sharpness has reduced when you went from just the regular plot to softmax plot, right? In fact, this plot is less sharp. What we can do is we can introduce a temperature parameter whose value is usually between 0.01 and 0.2, where we divide these similarity scores by this temperature score. So scaled similarity scores, we can say this is equal to the current similarity score divided by temperature. And if I want to construct it for all the rows, I can just say, because the denominator is constant, $G $2, and then just drag like this. Now the scale score will be 0.1 will become 0.1 divided by 0.1, which is 1. 0.2 will become 0.2 divided by 0.1, which is 2. 0.8 will become 8. And then I can take the exponent of 1, exponent of 2, and exponent of 8, resulting in these numbers. So sum total of these numbers is 2991, and then the softmax will be 2.7 divided by 2991, 7.3 divided by 2991, 2980 divided by 29, and then now my numbers are like this. Now this resulted in a very sharp probability distribution. So what happened? You think about what happened. The amplitude of softmax for correct pairs have now increased. So this 0.8 became 0.99. Amplitude of similarity scores for incorrect pairs have now reduced. So this 0.1 became close to 0. 0.2 became close to 0. And now my loss will be, loss is equal to negative log of this. So now look at the loss. So loss is highest for those 2 points with least similarity with the anchor. Loss is so the loss is highest, so 3 and 2. Loss is lowest for the item with the highest similarity with the anchor. So here for this, the loss is 0.004. We can amplify this loss even further by reducing the value of temperature. So if this is 0.06, then see you are further amplifying the loss. Softmax becomes even more sharp, and the loss will become, this loss will be much smaller, very close to 0. These two losses are amplified. If you go further down, see again the losses are amplified. If you go further down, 0.01, now the losses, now this exponent is so high that this is 0.0000, very small number. So it's almost close to 0. And these two losses are now amplified. So this is the purpose of using the temperature value. By playing with the value of the temperature, you can figure out how to make your softmax function much sharper and how to increase the difference between negative pairs and positive pairs. So now you see the distance between negative and positive pairs are this much. So negative pairs have values like close to 3 or 2. Positive pairs have loss value close to 0. If the temperature was 0.2 or let's say 0.02, then now the distance between the loss value between negative pairs and positive pairs are very high. So this is how you technically implement a contrastive loss. But this is only for the case where I is the anchor. But then J can be the anchor because let's say initially my I value was equal to 3. And let's say my total number of images was 10. Then with 3 as the anchor, I will have, or let's say total number of images are 100. And let's say I had originally 3 images, I equal to 1, 2, 3, etc. up to 10. And for each image, I created 10 augmentations, 10 with this, 10 with this, etc. and 10 with this, right? And now one of them will be the anchor. So the way I will construct the data set could be like this. I will pick one of these augmentations in my data set. So there will be one positive pair and remaining, let's say 90 are negative pairs. So I have now 91 data set points, n equal to 91, out of which I equal to 3 and j equal to something else is a positive pair. Remaining ones are negative pairs. And I can simply calculate the total contrastive loss to be, first calculate the negative logarithm loss for the case where I equal to 3 or I equal to 2 is the anchor. So let's say here I equal to 2. Then you construct the logarithmic loss for Li, where this is equal to L2. Then you construct the negative logarithmic loss where the anchor is I equal to 1. Because for I equal to 1 also you can construct positive pairs and you will have negative pairs. Positive pairs are constructed using augmentation. Negative pairs are there in the data set anyway. Then you can construct L1, and like that, how many ever data points you have, you can construct L1, L2, etc. up to Ln. And then your total contrastive loss is simply average of all of these. So L1 plus L2 plus L3 plus etc. up to Ln divided by n. So this is now the total contrastive loss. One question that you may have is, here we understand that we are taking, minimizing the cosine similarity, or rather minimizing the loss for pairs with highest cosine similarity. But what about negative pairs whose cosine similarity will be very less? Negative pairs are implicitly present in the denominator. So in the denominator, if let's say you are now considering a negative pair, then this number should be low, denominator should be high. So overall this number should be a small positive number, like let's say 0.01. So softmax probability score between two dissimilar pairs will be a low number. And if you take the negative logarithm of a low number, you will get a high positive number. And which means the loss, which is Li equal to anything, that will be a high number for those negative pairs. So this is how the loss is constructed. Similarity, the loss score will be highest if the similarity between positive pairs is low, and loss will be highest if similarity between negative pairs is high, or vice versa. If similarity between positive pairs is high, loss will be low. If similarity between negative pairs is low, loss will be low. And what similarity are we talking about here? Cosine similarity. And what are we doing with the cosine similarity? We are scaling it down. And after scaling it down, what are we doing? Scaling it up, rather. We are dividing by a temperature tau factor. And that tau value can be between 0.01 and 0.2. In general, these are all just thumb rules. There is nothing preventing you from trying out a different temperature value. And then when you take exponent, you can get softmax probability scores for positive pairs and negative pairs. And if you take negative logarithm of that, you will have the loss function. So now this is exactly what is done in clip. So now let's move on to clip. This we have already discussed. I just want to highlight one sentence. a low value of tau makes softmax sharper. This you saw. We used the lower we went, softmax became sharper and sharper. Loss became more and more contrastive. Then the model focuses on hardest negatives. You saw this because then the model was amplifying the loss for those negatives. A high value of tau makes the distribution smoother. It learns more gradually. This means the loss will not be, you will not be penalizing the negative models that much. On the other hand, if tau is very low, so let's keep the tau, let's start with tau equal to 0.2 and look at the loss for these two. Loss is not that high, which means you are not penalizing the model that much. But if the temperature is 0.01, for the same mistake, meaning for the same cosine similarity score, you are now penalizing the model so much. The loss is 30 and 26 for negative pairs. All right, so this is what it means by smoothing, using smoothing or making the distribution sharper by using the parameter tau. Now with this knowledge, let's get into how contrastive learning was used in CLIP. So the full form of CLIP, which was the model used in CLIP paper, is contrastive learning image pre-training, CLIP. So the idea of contrastive learning that we discussed so far was just for images. So you can teach a model to understand that, oh, all these images are dogs, but these are at the same time not cats. These are not pigeons. These are not something else, right? So this was contrastive images for a model to learn better and better representation of images. But in vision language model, we know that what we are trying to achieve is alignment between encoding of a text and encoding of an image. So if the model sees the picture of an apple and a text that says apple, both of them should have similar representation. So this figure is directly taken from the CLIP paper, and this is a very famous figure. If you simply search VLM, vision language model, in Google, it's very likely that this will be one of the figures that will pop up at the top. And here what you see is you have a text encoder and you have an image encoder. You will have let's say n items in the text. So let's say you have n sentences, Pepper the Aussie pup, and something else. And let's say you have n images here. You can construct encoded representation of each of these images. So I1 is the encoded representation of image number 1. I2 is for image number 2. Like that, IN is for image number n. Now, what are these I1, I2, I3, etc.? They are all different vectors. So now we have n images, and corresponding to n images, you have n vectors produced by the image encoder. Similarly, you will have n texts. What are these texts? These texts could be captions of these images. So this could be the caption of the first image. The second item would be the caption of whatever is the second image. So you will have n images and n captions. I'm just giving an example. Now these n captions also, which are text, can be converted into n vectors. So these text vectors, let's call it as T1, T2, T3, etc. up to Tn. So you have n text captions and you have n embeddings or n vectors constructed through the text encoder. Now this whole thing is not the vector, okay? Please don't get confused. This whole thing is just a representation of the fact that there are n different text items here. Now what are we trying to do? If the first item here and the first item in this set of images, they are caption and image pair, then the similarity between I1 and T1 should be very high, and similarity between I1 and T2 should be very low. Similarity between I1 and T3 should be low. I1 and Tn should be low, which means if we are talking about cosine similarity, I1 dot T1, and let's assume for a moment that these are normalized vectors, then I1 dot T1 should be as close to 1 as possible. I1 dot T2 should be as close to 0 as possible. I1 dot T3 should be as close to 0 as possible because this T2 is the caption for second image, T3 is the caption for third image, Tn is the caption for nth image, and they are different images. Those captions do not really represent what is present in image number 1, which means I1.T1, I1.T3, I1.Tn, all of them should be ideally 0 or close to 0. And conversely, T1, now look at caption number 1. So I1.T1 should be high because this is image 1 and caption 1. They should have very high similarity. So this again should be high number, close to 1. But I2.T1, I3.T1, like that, IN.T1, they all should be low because caption T1 ideally suits image number 1 the best. Caption number T1 does not suit image 2 or image 3 or image N, assuming there is good diversity in the images and corresponding captions. So now this is again an example of contrastive learning where you are trying to maximize the similarity between positive pairs. So this I1 and T1 is a positive pair. I2 and T2 are positive pairs, but I1 and T2 are negative pairs. I1 and T3 are negative pairs. I1 and Tn are negative pairs. So all these cells that you see here are dot products of vector representation of image and text where they are all negative pairs. So, but all these blue ones are positive pairs. So you want to maximize this value, this dot product value, such that when you take the softmax and then you take the loss, which is negative logarithm, these numbers should all result in close to zero loss, and these numbers all should result in a high value of loss. Now, there are two ways in which we can construct the loss. One is we can consider, so now here, if we look at pairs, it's not image pair anymore, right? In the previous example, it was pair of positive images or pair of negative images. Here, the pair is image text pair. So I1 T1 is an image text pair. I1 and T2 is another pair. I1 and T3 is another pair. So now we should look at for every pair or rather for every image and text pair. So let's say I want to construct the vision language model such that alignment between I1 and T1 should be highest. Then there are two ways in which I can construct the loss. One is I say that the similarity between dot product of I1 and T1 should be highest, and dot product between I1 and any other T, so any other T meaning T1, T2, etc. up to Tn should be highly dissimilar. So dot product between them should be very low. This is one way in which I can say. One more way in which I can say is dot product between T1 and I1 should be very high, which can be written as I1.T1 or T1.I1, both are same. But at the same time, dot product between T1 and any other I should be low. So this should be high, but all these should be low. So in one case, I1 is my anchor. So in the first example, which I said, if you look at it from this row perspective, I1 is the anchor, T1 is the positive pair with I1, but T2, T3, etc. up to Tn are all negative pairs compared to considering I1. Conversely, if I now consider text where T1 is the anchor, I1 is the positive pair, but I2, I3, etc. up to In are negative pairs. So we can construct two losses, one from the perspective of the text and one from the perspective of image. So this equation very nicely summarizes the two contrastive losses that we just discussed. One is image to text contrastive objective, where xi is image, yi is the text embedding. Then sigma is the equivalent of temperature. So this we saw earlier as tau. Now let's see this equation. So exponent of xi tau yi. So this is what? Xi transpose, not xi tau, xi transpose yi is the dot product between xi and yi. So this is embedding of image, and this is embedding of text, and this is temperature. So this is the softmax probability score. Whatever is there in this logarithm is the softmax probability score for ith image and ith text embedding to be the correct pairs. So here this is xi transpose dot yi divided by sigma. So these are now the correct pairs, image number I and text number I. The denominator is the sum of exponents of xi transpose and yj. So xi transpose will remain the same. So now what is the anchor here? Anchor is the image. So you are comparing now this image. You are comparing this image with this T1, T2, T3, etc. up to Tn, right? So in the denominator, you will take the dot product between I1 and T1, I1 and T2, I1 and T3, I1 and T4, and I1 and Tn if I is equal to 1. And then you will take negative logarithm. Now that is with the case where the anchor image is image number 1. But anchor image can be image number 2. Then we will move on to the second row. So now if we move on to the second row, if I2 is the anchor, then you can construct dot product between I2 and T1, I2 and T2, I2 and T3, I2 and T4, etc. up to I2 and Tn. And that will look like sigma where I runs from 1 to n. So here the contrastive loss is in the numerator you are comparing between two positive pairs. In the denominator you have positive and negative pairs. Do you see that this is xi and this is yi? And by doing this, if you minimize the loss, essentially what that means is the dot product between xi and yi will be very, very close to 1. The dot product between xi and yj will be very close to 0 for all values of j that are not equal to I. But then why do we have this sigma outside the logarithm? Because we have to do the contrastive loss where image number 1 is the anchor in the first case, image number 2 is the anchor, then image number 3 is the anchor, and then all these losses we have to sum up and then divide by n. So essentially this is like constructing loss along the first row here first, along the second row here next, the third row then fourth row, and then nth row, and then all these loss values you add up and divide by n. So you will get an average of the loss. Now this is the loss where you are converting image into, or you are comparing a particular image with text. Now you have the opposite. You can do it column wise also. You can keep T1 as your anchor, and then I1, I2, I3, etc. up to In will be your will be the images that you are comparing your anchor against. And then that is the second formula. So here you have text to image contrastive objective. So you have multiple images that you are comparing against a given text. So exponent of, now look at this, x and y has flipped. Yi transpose. So now this is the transpose of ith text embedding. You are comparing it with ith image embedding, and this is the temperature parameter sigma. So the numerator is basically dot product between ith text embedding, ith image, y is text embedding. So this is the dot product between ith text embedding and ith image embedding. That is the numerator. Denominator is the dot product between ith text embedding and all image embeddings. So yi will remain same because here sigma is over j, it's not over I. Then you will take dot product between text number 1 and image number 1, then text number 1 and image number 2, text number 1 and image number 3, text number 1 and image number 4, and so on. So then you will get the first item. So this will be the loss when you compare text 1 and image number, any image. Then why do you have this outside sigma? Outside sigma is because now you can compare text number 2 with image number 1, text number 2 with image number 2, and so on. So now text is the anchor. And for each of this inner loop, text number 1 or text number 2, or depending on what the value of I, that will be the anchor. In the previous example, inside this sigma, image number I will be the anchor, where I can be whatever the value that you are assigning in that particular loop. And why do we have negative sign here? Because you are taking negative logarithm. Why do we have 1 by n here? Because you are summing all the losses, all the negative logarithmic losses, and you are dividing it by n. So it's like a average loss. So this is what is done in contrastive learning to maximize the similarity between pairs of image and text that are supposed to align, and to minimize the similarity between pairs of image and text that are not supposed to align. And then what you do with these two losses is your final loss will simply be an average of these two. So L is equal to Li to T, which is image to text, plus L text to image divided by 2. So this will be your final contrastive loss, and this is also called symmetric loss, because you are considering the loss where you are looking at image compared to every single text and text compared to every single image. And before we wind up, one last question that you may naturally have is, what if I have more than one caption that is rightly suited for an image? So let's say I have multiple images of dogs, And by default, let's say caption number 1 and image number 1 are the pairs, and let's say image 3 is also like a dog, and caption 3 is also something related to a puppy. Then ideally for image number 1, caption 1 and caption 3 both are suitable, right? So for image number 1, caption 1, T1 is suitable, T3 is also kind of suitable, right? So this is one limitation with clip, because it still pushes away T3. It still tries to reduce the dot product similarity between I1 and T3. So it is one limitation of clip, but clip was seen to work extremely well despite this limitation, because the data set was so huge. They had around, I think, 400 million image text pairs. Let me just open clip paper once quickly. So 400, yeah, so they had basically image representation from scratch on a data set of 400 million image text pairs collected from the internet. So this was one reason why clip works so well. So I hope this brings you a lot of clarity about how contrastive learning works if you simply consider image pairs to identify good image pairs, and that indirectly helps you create good representations in vector form for images. And for vision language models, I hope you understand how a loss function is constructed using the same idea of contrastive learning in the clip paper. So with that, let's wind up today's lecture. In the next lecture, we will see how to construct a nano vision language model completely from scratch. So we will build it from scratch. We will train it with our own data set, and the loss that we will use in this model will be a clip-like contrastive loss. So see you soon in the next lecture. Take care until then. Bye.